Okay, states of matter. Chapter 10.
So I wanted to talk to people about the different states of matter, solid, liquid, and gas, using water as an example. But I thought first I better be sure that we're all on the same page about what water is made of. What's water made of? Water? What makes water? Water. Okay, what elements does it take to make water? H2O. So what does that mean? It is water. What elements? Water and cold. Water plus cold. But what does the H and the O mean? Something and oxygen. Something and oxygen. Hydrogen. There you go. Hydrogen. Hydrogen and oxygen. What's the two mean? Hydrogen oxygen. And the two, H2O. Why do we say tooth? I don't know. It's two molecules of hydrogen and one of oxygen. There you go. So that makes what we call a water. Come on. two atoms of hydrogen and one atom of oxygen makes a water molecule. I know, the word was like on the tip of your tongue. I guess we got there in the end. So what's the difference between solid and liquid water? So the temperature of it. It's not cold. Ice is frozen. What does it mean to be frozen then? Cold. Liquid water is no good for skating on. Ice is great. Nothing up with temperature. So everyone recognizes that temperature is important in determining whether the water is ice or liquid. Well, what's actually happening between the water molecules? What's the difference between water and ice? It's frozen. What does it mean for something to be frozen? It's solid. Well, what does it mean for something to be solid? That it's like a brick. It's like a brick. And what makes it like a brick? What's happening in there? I don't know. But what makes it a solid versus a liquid? Well, in this case, lots of pipes going underneath. But that makes it very cold. Makes it very, very cold, yeah. But what's actually happening to the little bits of water? They're attaching to each other. They're attaching to this is all that we guess right here. I imagine they're attaching to each other. They're forming a more solid interpiece. You cool liquid water down, and then at some point, what happens to it? It slows down, freezes, and stops moving. The molecules become frozen. How do they become frozen? They join together. They accumulate.
You can do it.
Coagulate is not the technical term for it, but in ice, the water molecules are basically fixed in place. They form a crystal lattice where their only motion is vibrating. So what happens if we heat up the ice? Like what happens when a solid melts? They all bounce out and what are we talking about? What are they doing? In science, you draw little circles. What are those little circles? Oxygen. Are they just oxygen? Hydrogen oxygen. And the two. And the two. The temperature is higher. So the particles, they're less stable. Yeah. Less stable? Less stable. Less free to move around. That sounds right. So they become separate and they are allowed to move around. And in gas, maybe they're further apart. Is that what we're okay? Yeah, fantastic. This guy's nailed it. All right, that makes sense. That's awesome. All right. So in liquid water, the water molecules not only vibrate, they can also rotate and slide past each other. And this is what allows the substance to flow. At even higher temperatures, the water molecules become free of that liquid and turn into water vapor. In that state, they are very, very far apart and moving very quickly. So the major differences between solid, liquid, and gas are the motion of the particles and the distance between them. Of course, you may want to meditate on these differences some more. What about the difference between a solid, a liquid, and a gas? Oh, that's easy. I teach meditation. It's all about as you de-excite something, so you de-excite the mind, you get more orderliness. As you de-excite water vapor, you get water. As you de-excite water, you get ice. More orderly. So that the molecular structure becomes more orderly. That's the difference. That sounds quite reasonable. How do you de-excite something? Well, in this case, you actually remove energy from it. In human beings, you calm their minds down with meditation. And that works. You get excited. Yeah. Does that mean if I meditate too much, I might turn into ice, though? No, but you'll generally become cool. Good answer, Sam. Thank you so much.
Okay, so we're going to start by looking at the kinetic molecular theory of matter. This is a way that we describe the behavior of molecules in different states. Blah, blah, blah. All right. So the kinetic molecular theory is based on the idea that particles of matter are always in motion. Keep in mind that new vocabulary appears in red. The KM theory can be used to explain the properties of solids, liquids, and gases in terms of the energy of the atoms and the forces that act between them. This is always going to be a battle between the energy of the energy of the particles. I'm going to call them particles instead of atoms or molecules because it could be either one. The energy of the particles versus the attractive forces between them. There's always a balance, and that's what determines whether something's a solid, liquid, or gas.
The kinetic molecular theory is the theory that all matter is composed of atoms and molecules that are in constant motion. The particles move at one energy. The more energy a particle has, the more and faster it will move. In solids, such as ice, the molecules hardly move at all in a regular pattern because the energy is low and the molecules are tiny atoms. In a liquid like water, the molecules have freedom to move around and have more energy. Liquids have the ability to fill any shape of any container they're pushed in. In gases like steam, the molecules have the most energy. Gases can expand and compress to fill any container. All matter contains atoms and molecules that are moving. The warmer the temperature, the more energy these particles have, and that is the kinetic.
All right, so this theory provides a model of an ideal gas. It is based on 5 assumptions. And before I talk about the 5 assumptions, we have to define an ideal gas that is an imaginary gas, so it does not exist, but an ideal gas would perfectly fit all 5 assumptions of the KM theory. Okay, assumption number 1, gases consist of large numbers of tiny particles that are far apart relative to their size. They typically occupy a volume about 1,000 times more than the volume of a liquid or a solid. This is because they are much farther apart than in a liquid or solid, and this accounts for gases' lower densities as well as their compressibility. Assumption number 2, collisions between gas particles and between particles and the container walls are what are called elastic collisions. An elastic collision is when there is no net loss of kinetic energy. The kinetic energy is transferred, but the total kinetic energy remains the same as long as the temperature is constant. So this idiocy that you see in the video explains an elastic collision because you have 4 dumbasses that each have a yoga ball and they're all moving towards each other. So each of those 4 have kinetic energy. Now, when they hit, you see that 3 of them, the kinetic energy is almost lost, and all of that kinetic energy is transferred to the poor sop on the floor now. So that is a perfect example of an elastic collision. There's no net loss of kinetic energy, it's transferred. So all 3 guys, the energy of all 3 guys was transferred to that one. Assumption number 3, gas particles are in continuous rapid random motion. They therefore possess kinetic energy, which is the energy of motion, and they move in all direction. So the kinetic energy has allowed the gas particles to overcome the attractive forces between the atoms. Assumption number 4, there are no forces of attraction or repulsion between gas particles. So imagine gas atoms are like billiard balls. They hit each other and bounce off. And finally, assumption number 5, the average kinetic energy of gas particles depends on the temperature of the gas. The kinetic energy of any moving object is shown by Ke equals 1/2 mv squared. I'm assuming you have covered that in physics already, where m is the mass of the particle and v is velocity. Now, the Km theory only applies to ideal gases, which, like I said, don't actually exist, but you can get real gases to behave almost ideally if the pressure is very low and temperature is very high. So the attractive forces between particles would be very minimal under these conditions. If you have very low pressure, very high temperature, then you can get real gases to behave almost ideally. So how does KM theory account for the physical properties of gases? Let's go through the physical properties and figure out which part of the KM theory applies to describe this behavior. So the first property of gases is expansion. They do not have a definite shape or volume. They completely fill any container and take the shape of that container. So the KM theory assumptions that apply here is assumption number 3, that gas particles move rapidly in all directions, and assumption number 4, that there's no significant attraction or repulsion between them. That's expansion. The second property is fluidity. Because attractive forces between gas particles are insignificant according to assumption number 4, the particles easily pass each other. This ability causes gases to behave similarly to liquids, and because they have the ability to flow, both gases and liquids are referred to as fluids. The next property is low density. Like I said, gases are about 1/1000th of the density of the same substance that it is in liquid or solid form. And this is because of assumption number 1, tiny particles that are really far apart. And then that rolls into the next property, which is compressibility. During compression, the gas particles, which are initially very far apart, assumption number 1, are crowded closer together. So the volume of a given sample of a gas can be greatly decreased. And next we have diffusion and effusion. Gases spread out and mix with one another even without being stirred. So if the stopper is removed from a container of ammonia in a room, the ammonia gas will mix uniformly with the air and spread throughout the room, and you'll probably have a face like The Rock has right now. The continuous and rapid motion of the ammonia molecules from assumption number 3 carries them throughout the available space. This mixing of the particles of two substances by their random motion is diffusion, which we learned about in biology last year. The rate of diffusion of one gas through another depends on 3 properties of the gas particles. 1, their speeds, 2, their diameters, and 3, the attractive forces between them. So the stronger the attractive forces between the particles, the slower diffusion will be. And next is effusion. Effusion is just diffusion through a tiny opening. And the rate of effusion is directly proportional to the velocity. So the faster the particles go, the faster effusion occurs. So when does a gas deviate or go away from ideal gas behavior? When the particles are far enough apart and have enough kinetic energy, most gases behave ideally. A real gas is a gas that does not behave completely according to the KM theory. Now, in 1873, Johann van der Waals accounted for the movement away from ideal behavior by pointing out that particles of real gases occupy space and apply attractive forces on each other. This is a violation of assumption number 4. This is what makes most gases not ideal, because even in noble gases, we have London dispersion forces. If you remember from chemistry last year, when I talked about the fact that electrons go around the nucleus. So at any one time, you might have a higher concentration of electrons on one side than the other, and that creates a temporary dipole. So you might have one side of the atom being slightly negative and the other side slightly positive just by the movement of electrons. So if I say that gases can behave close to ideal at very low pressure and very high temperature, then obviously the opposite is true. At very high pressure and very low temperatures, you're going to have the greatest deviation or the greatest moving away from ideal gas behavior. So under those conditions, high pressure, low temperature, the particles are closer together and the kinetic energy will not be high enough for them to overcome their attractive forces. Remember, I said it's a battle between kinetic energy and attractive force that determines the behavior of a substance in whatever state that they're in. So the KM theory is more likely to hold true for gases whose particles have little attraction for each other, like the noble gases. They're monoatomic, they are nonpolar. And the more polar a gas's molecules are, the greater the attractive forces between them, and the more they will stray or deviate away from ideal gas behavior.